This is a tutorial on row reduction of a matrix using row operations into echelon form and then into reduced echelon form. When performing this on an augmented matrix, which consists of a coefficient matrix of a system of linear equations concatenated with the solution vector, the row reduction creates a system with the same solution set, but in a different, more convenient form. The echelon form can tell a lot about the properties of a system of equations. The reduced form makes writing the solution set very simple. This video will not go into the implications of the echelon and reduced echelon forms. The focus will be the actual row reduction procedure. So suppose we start out with a system of equations like this. Negative 2x2 plus 4x3 minus 2x4 minus 6x6 is equal to minus 4. 2x1 minus 4x2 plus 14x3 minus 6x4 minus 2x5 minus 10x6 is equal to negative 4. 2x1 plus 3x2 plus x4 plus x5 plus 14x6 is equal to 19, and negative x1 minus 2x2 plus x3 minus x4 minus 8x6 is equal to negative 9. So we have 6 unknowns and 4 equations. We can write this in the standard matrix equation form by creating the coefficient matrix for this, which is going to be the coefficients. So 0, because there is no x1 in the first equation, minus 2, 4, minus 2, 0, minus 6, then 2, minus 4, 14, minus 6, minus 2, minus 10, 2, 3, 0, 1, 1, 14, and negative 1, negative 2, 1, negative 1, 0, negative 8. That's our coefficient matrix. Then we have our vector of unknowns, x1, x2, x3, x4, x5, and x6. And that's equal to our vector of solutions b, which is negative 4, 19, and negative 9. From this, we can form the augmented matrix of the system by concatenating the coefficient matrix with the solution vector. So that would be 0, negative 2, 4, negative 2, 0, negative 6, negative 4, 2, negative 4, 14, negative 6, negative 2, negative 10, and then the solution negative 4, 2, 3, 0, 1, 1, 14, and 19, and negative 1, negative 2, 1, negative 1, 0, negative 8, negative 9. So this is the matrix that we're actually going to be working with. And so now we want to perform reduction on this matrix. In order to do that, we're going to use row operations in order to create the two matrix forms mentioned before, the echelon form and the reduced echelon form. The three operations are shown right here. We can interchange two rows of the augmented matrix we can multiply all the entries in a row by a non-zero constant, and we can replace one row by the sum of itself and a multiple of another row. So let's see how this will work on our example. We'll start off with the matrix that we have. 0, minus 2, 4, minus 2, 0, minus 6, minus 4, 2, minus 4, 14, minus 6, minus 2, minus 10, minus 4, 2, 3, 0, 1, 1, 14, 19, minus 2, minus 1, negative 1, 0, negative 8, negative 9. So this is our original matrix as it's written right here. And the first thing that we want to do is to get a non-zero entry into the top left position. So we're going to use a row interchange, and the way we're going to denote that, so row equivalence is shown by this kind of a tilde, and we're going to write the exact operation that we perform on top of it. So in this case, we're going to swap row 1 and row 2. And the resulting matrix is then going to be just as we expect. And the other two rows remain unchanged. And now one more thing we want to do is create a 1 in this top left position. So we're just going to divide every entry in row 1 by 2. So to write that operation, we're going to say that 1/2 row 1 is going to then go into row 1. So the resulting matrix, just divide the first row by 2. And the other rows remain the same. Now, we're going to try to create zeros below the first non-zero entry in row 1. So specifically, we're going to use this entry in order to create zeros everywhere below it by using the row operations. So to do that, well, there's already a 0 in row 2, so that's good for us. To create zeros below the 1 in the first column, we're going to use the third operation, replace one row by the sum of itself and a multiple of another row. Specifically, in this case, we're going to take row 3 plus negative 2 times row 1 and put that into row 3. So, row 1 remains unchanged. Row 2 also remains unchanged since we didn't have to do anything to it at this point. Row 3 gets replaced as we mentioned here, so just performing that addition, we're going to get a 0 here, which is exactly what we were trying to create, and then we get 7 minus 14, 7, 3, 24, and 23. And then for the last row, the fourth row, we're just going to add row 4 and row 1 and put that into row 4. So then again we get a 0 here, which is our goal. Minus 4, 8, negative 4, negative 1, negative 13, negative 11. So now we have this matrix, which is again row equivalent. That is, we just performed row operations from the beginning to here. The next step, since we have all zeros below this first entry, is we're going to try to do the same thing to the rest of this matrix, that is to the submatrix that's left under here. In other words, what we're going to do is we're going to ignore these entries and perform the same thing we just did to everything that's left. The reason we can do that, we can ignore this column, for example, is because every operation that we do on rows 2 through 4 is not going to affect the first column, since all of their entries are zeros. Therefore, taking any multiple, interchanging any rows, or adding multiples of rows to other rows will not change the first column of these second, third, and fourth rows. So we're going to do the same kind of thing. Again, we want to create a 1 in the top left corner. In this case, we already start off with a non-zero entry, so we can just scale it. And so we'll put negative 1/2 of row 2 into row 2. Now row 1 is not going to change. As we mentioned, we're going to leave that alone. So I'll just denote it like that, and also the first column. The second row gets scaled and becomes 1, negative 2, 1, 0, 3, 2. And we don't do anything for the moment with the other rows, so they remain the same. Now we're going to try to create zeros below this entry over here. So the same way that we did before, up here, we're going to do the same thing here. So we're going to take this and we're going to create zeros below it. So now the operation that we're going to perform is going to be taking row 3 and adding negative 7 times row 2 to it and putting that back into row 3. So once again, the first row and the first column are blocked out, they don't matter. The second row remains as is. And we're going to perform this operation now and replace row 3 with it, and that's going to give us 0, 0, 0, 3, 3, 9. And for the fourth row, we're going to say that's going to be row 4 plus 4 row 1 is going to go into row 4. So that will give us 0, 0, 0, negative 1, negative 1, negative 3. Now, since we created these zeros, we're going to look for the next non-zero entry in the following row, which is in this case 3. And we're going to block out everything else to the left and on top of it. So now this, and these are also zeros, so they won't affect things if we do row operations on row number 3 and 4, none of these zeros are going to matter, so we're just going to focus on this submatrix now. So once again, we'll start off by scaling, and we'll say that 1/3 row 3 replaces row 3. And so again, we have these spots that don't matter. And we're going to get 1, 1, 3, -1, -1, -3. So then, one more step is to say that row 4 plus row 3 replaces row 4. And we get, after blocking out the appropriate rows and columns, row 3 is unchanged, so it's still 1, 1, 3, and the last one becomes 0, 0, 0. So this altogether is equal to 1, -2, 7, -3, -1, -5, -2. That's what we had blocked out by the light blue over here. Then the next row is 0, 1, -2, 1, 0, 3, and 2. That was blocked out by the yellow, and of course these corresponding zeros that were in the columns. And finally, the result from here is 1, 1, 3, 0, 0, 0. So now we are actually in an echelon form, in the first form that we wanted to get into. So this is in echelon form. What this means is that we have a non-zero entry as the first entry in each row, and everything before it is zeros. Everything below these first non-zero entries is a 0, and all 0 rows are below any non-zero rows. These first entries here don't have to necessarily be a 1 in the echelon form. They can be scaled by anything, and therefore there isn't just one echelon form for any given system of equations, but there is only one reduced echelon form, and we'll see that shortly. So these positions with the non-zero entries are called pivot positions, and the corresponding columns are the pivot columns. Everything that's not a pivot column is a free variable. I don't want to focus on that though in this video, because the point is just to show an example of the row reduction and not to necessarily talk about the implications. So now we want to get into the reduced form. So the first thing we're going to do is actually we're going to work backwards and create zeros above all of the pivot positions. So just like before we used the leading entries to create zeros below them, we're going to do the same thing to create those entries to zeros above them. So in this case, we're going to start with this position, and we're going to create zeros above it by using the same kind of row operations as before. So we're going to say that row 1 plus row 3 replaces row 1, which is going to be, since we're adding row 3, the first 4 entries are going to stay the same since there are 4 zeros leading up to it. So it's going to be 1, -2, 7, -3. And then this part becomes a 0, and we have -4, 1. The rest are going to remain unchanged because we already have a 0 in this location above here, so we don't need to do anything to create that 0. And the fourth row stays as all zeros. Now we're going to use our next pivot position, this one, to create zeros above it. In this case, again, this will be just one operation. We will take row 1 plus 2, row 2, and replace row 1 with that. So that's going to be 1, 0, as we want, 3, -1, 0, 2, 5. The second row unchanged. And likewise for the rest. And this is our reduced echelon form. It's characterized by the fact that every leading entry, every pivot, is a 1, and every entry both below and above each pivot is a 0. This is a unique form for a system of linear equations, and you will get to it no matter which one of these other systems of equations you start with, whereas the echelon form is not necessarily unique since you can scale each row. This is going to be unique. You have a 1 in the leading positions, in the pivot positions, and you have zeros everywhere above and below them. Taking one more step in this solution, we can see why this form is nicer than the original form by writing out the solution set. So using this form, we can write out our equations, which are going to be x1 plus 3x3 minus x4 plus 2x6 equals 5. That is, remember that this is showing the augmented matrix where our variables correspond to the columns x1, x2, x3, x4, x5, x6, and our solution vector b. So in the first one we had 1x1 plus 3x3 minus x4 plus 2x6 is equal to 5. The second equation, x2 minus 2x3 plus x4 plus 3x6 is equal to 2. Then we have that x5 plus x6 is equal to 3. So we get these three equations which show the basic variables, that is the pivot column variables, in terms of the free variables and the constants. So more specifically, this can be rewritten as x1 equals 5 minus 3x3 plus x4 minus 2x6. x2 is equal to 2 plus 2x3 minus x4 minus 3x6. And x5 is equal to 3 minus x6. So again, we have our basic variables, the pivot columns, in terms of the free variables and the constants. And then this can be written as a solution set. X is our variable, which is just again x1, x2, x3, x4, x5, and x6. And that is going to be equal to as we just found, x1 is 5 minus 3 x3 plus x4 minus 2 x6. x2 is 2 plus 2 x3 minus x4 minus 3 x6. x3 is just x3, it's a free variable. x4, same thing. x5 we know is 3 minus x6, and x6 again is free. And so this can be finally written as one solution vector, particular solution to the system, 5, 2, 0, 0, 3, 0, so just all the constants by themselves, plus the first free variable, x3, times its corresponding entries in here, so that's a minus 3, a 2, a 1, since it's equal to itself, and then 0, since it doesn't appear in the definitions of x4, x5, and x6. Then the next one, x4, and its corresponding vector of 1, negative 1, 0, 1, 0, 0. And the last one, x6, which is negative 2, negative 3, 0, 0, negative 1, 1. And this is the solution in parametric vector form. Overall, we've taken a system of equations and replaced it by another system of equations with the same solution set. The new form makes many desirable properties of the system easy to find and also makes the solution set easy to write. There are very many applications of row reduction, so it's a good idea to practice it. After some practice, the row operations become much easier to perform and the whole procedure becomes easier.